kind of know stuff now. Then we did two mathematical calculation about the geometrical similar forms and alterations in the same forms. So now today what we will do, we will try to learn how can we work with those pump performance curve and how can we find which pump is suitable for our need, or whatever system we have, which pump we need to use for this one. Okay, now we need to understand few new terms again. You will see, you already know those terms, it's just you didn't know the name. So that's what we will do today. If we get time, we'll start working on mathematical problem. If we don't get time, that's okay. So just bear with me. Again, today we will be doing some literature review about the pumps. Okay. So for the very first thing, we need to know different head terms in pumping. The first one is, if you have a pump here, okay, what is the function of pump? It will take the fluids from one point and it will deliver it to the other point, right? Now, the distance between pump and the point from which it is taking the fluid, that is actually called static suction lift. It's like for which distance that pump is suctioning any water or any other liquid, okay? And from this point, obviously it is delivering the fluid to some other points, right? Now that distance, like from this point to this point, it is called static discharge head. Now you will have the same case here as well, but if you look at C, you will see the initial, like from which point the pump is taking water or any liquid, that is actually above the pump. So pump is taking water from that, and then from this point is delivering water into some other points. So the position can be different, but it will be always static suction lift and static discharge head, and it can be positive and negative. Okay. Now the very final one, the total distance between these 2 points. Suppose this one is A and this one is B, and if you have a datum that is ZA, we know that, right? And from this point, that is ZB. Now that ZA and ZB, that is actually the elevation difference between these 2 points, right? From where it will take the water to where it will deliver the water, right? And this delta Z is called total static head. So we knew the delta Z term, but we didn't know the name of this term, right? So that is the total static head. And if you look at all the setup here, total static head is actually the summation of what?
Static suction lift and the static discharge head.
Correct. So total static head is the total difference between 2 points from where the pump will get water and where it will deliver. Basically, it's the summation of static suction lift plus static discharge head. Okay. And you can see that static suction lift, it can be positive or negative. But the equation doesn't change. If it's negative, the negative sign will take care of itself. So you don't need to do anything. Okay? Okay. Now, once we know that, we will use these head terms to get the expression for the pump head. Okay? Now, before we start working on that, in which equation we use the pump head? Like in which equation you see the pump head term? The energy equation, right? If we want to apply the energy equation in between 2 points, we see a term called pump head, right? So basically, if I just write down the equation from the very beginning, it's energy equation in between any 2 points. The equation is P1 over gamma V1 square over 2G Z1, and the pump head. If we have a turbine, we will have the turbine. If not, that's okay. So P2 over gamma V2 square over 2G Z2 head loss, right? Now from this equation, if you just rearrange the whole thing, you will get this expression. That is the rearrange expression for pump head. Now in this expression, we have velocity, we have pressure, we have elevation head, we have head loss. So this is the general expression, but you already know there are hundreds of situations where we don't have any pressure, where we know the velocity is 0, something like that, right? So we will try to come up with 2 expressions for 2 most common cases we will encounter for this course. So this is the most generic expression. Okay. So what we will do, we will try to come up with the head loss expression for 2 different systems which we encounter most of the time. The first one is if we have 2 open reservoir system. Okay. So for this case, if this point is A and this point is B, what is the PA and what is the PB? At point A, what is the pressure?
0.
What about PB?
0.
Okay. Now for VA and VB, VA is again 0. What about VB? 0, because it's open surface and the velocity is very, very negligible, right? Now if I apply this to this general expression, it will be V is 0, V1 is 0, P2 is 0, P1 is 0. That means pump head equals to what? 0 plus 0 plus, and Z2 minus Z1 is delta Z plus head loss, right? And this will be pump head delta Z plus head loss. So you see, we started with a very long equation, but we came up with only 2 terms here, right? And for this head loss, which equation you can use for this head loss? Any equation or any specific equation? Like when I say any equation means Hazen-Williams and Darcy-Weisbach equation. We can use both?
Yes.
Yes, we can use both. And we will just write down that head loss equals to K Q to the power N. And you can use Darcy-Weisbach equation, Hazen-Williams equation. It doesn't matter which one you will use. It will, based on the available data set, you need to decide which one you can use. Okay. Now, since you know the steps, can you work on the next one when you have 1 open reservoir and 1 pipe end? Okay. Can you work on that part by yourself? You can discuss with your friend. You can work together. That's okay. So for the next one, you have 1 open reservoir, 1 open end of the pipe. So I will check with you after 2 minutes. You have 2 minutes to work on that.
So we already know for since it's open, that's going to be equal to VA is going to be equal to 0. So we're trying to
So we are trying to find the expression for this one. Okay. This one is open reservoir. Okay.
But the velocity is 0 at B. So you have Z plus B2 plus M plus. Oh, B2 squared over 0.
Okay, everyone please work on that, either alone or together with any friend. I will check with you after 2 minutes what is the expression for that. What will be the only difference?
You're ruining my chances of getting a boyfriend.
You gotta pay this
At B, the velocity of B. Wait, B is not open to Yes, it is. It's an open pipe. Does that count? Yeah. Yeah.
If I consider that is open, not that I can consider that.
What? Oh.
Oh.
Alright.
Wait.
6'11".
That may be
The tallest. What kind of post is that? Isn't that kind of cool? Dude, you're running out of something. You're like, someone, let's give the tallest guy one beat. Hey, you don't discriminate on height either. Because that was gonna be the next article.
Wait, no, Ben, you gotta open it.
Yes, what is the only difference here?
You have this one.
You have one velocity, okay. Okay, there can be one variation also here. Okay, anyone else has anything to say about this one? What is happening? Why everyone is going out? That was not that hard. That you need a break. Okay, so for this one, I said that you can open that an open reservoir, but in real it can be a pressurized situation. In that case, PA will be not 0 if it's the pressurized situation. If it is an open reservoir, which I ask you to consider, then the pressure is 0. What about the velocity? 0 or almost 0. At B, it's open to atmosphere. What will be the pressure? What about the velocity? The velocity is not 0. There will be something. So I will just keep that as VB because I don't know. So now if you again go back to that, V2 is VB square over 2G. V1 is 0. P2 is 0. P1 is 0. Z2 minus Z1 is delta Z. And head loss equals to K, Q to the power N. Right? So your final expression for pump head will be VB square over 2G delta Z plus HL. Say it again. You can be HL equals to KQ to the power N, so you can use that. Or you can directly use FL over DV square over 2G. Like what I'm trying to say doesn't matter as long as you can calculate head loss in any way. Okay? Now, these expressions, if you can remember, that's okay. If you can't, that is fine. But I always start from energy equation. And I recommend everyone to do that so that you don't miss something. So whenever you will start from the energy equation, you will always come up with this expression, right? If you know the basics. So if you can remember the final expression, that is fine. If you don't, that is fine also. Okay. Okay. So now we know few terms about few head terms about pumps. Now we will use those to get to know more about the pumps. Okay. Now here we have how many different systems we have here? 1, 2, 3, 4, 5, right? The last one is to open reservoir system. Here we have pipe end and open reservoir here. But if you consider this point, you have pipe end. Do you think you have a pressure? Like you need to consider pressure here? Pressure will be 0 or something else. There will be something else. If the H is the depth, the pressure will be gamma H. So P will be gamma H. So it will depend on which point you are considering, right? The same thing here, A and E, those are open, but at this point, you have velocity, you have some pressure. So you have velocity at D, you have PD, something like that. Now here, A is, it's a pressurized situation, so you have PA something, but VA is 0. At this point, if you work with this part, all the things are 0. But if you consider the pipe end, you will have a velocity, right? So what I'm trying to say that we can have millions of different combination with two different ends, right? Now, suppose we are using the same pump at every condition. Suppose you have a pump you bought, or we have a pump in lab, and we are using the same pumps in every condition. Now, the pump itself has some function, right? Like some specific function. Just think about any printer. Okay, you have a printer. What is the main function of that printer? It will print something, right? Now, it will print no matter what paper you are giving or feeding it, that printer, right? It will do something. That means that printer has some specific function criteria or performance characteristics. But from your side, from user perspective, if you use a glossy paper or if you use just this normal paper, you will have different experience, right? Now it's your choice. You will use glossy paper or this normal paper, right? So that means there can be two different type of criteria. One is for printer itself, one is from user perspective, right? So the same thing here, if we use the same pump, suppose this is pump, your section 2, so it is section 2. So pump section 2. We are using the same pump here, like pump section 2. Same pump here, here, here. So every time the pump is same, so it has some specific characteristics it is supposed to provide you. But if you look at here, suppose I have 4 cadets here and 1 cadet from the second row, you have different type of criteria. One of you said, no, I will use photo paper. Another one said, I will use glossy paper. Another one said, I will use A3. Another one said, I will use A4. So based on that, you have different system for your purpose, right? And just like that, for pump and system, we have two different curve or two different characteristics we can get. So for pump, all the characteristics, those are called pump characteristics curve, all the characteristics for user perspective, like whatever you have, that is called the system curve. I will write down all the definition, but just to give you the total idea, system curve is whatever you have in your system, and the pump curve is whatever the pump has. Okay, so we will deal with two different curve system here. Okay, and if you look at here, for each system, delta Z is different, right? Okay, so but every time, whatever curve you are trying to develop, it's the same equation. It's just for different system, you will have different magnitude, right? Okay, so I will just write down the system curve. The system curve is, it's a curve, oops, which will express or demonstrate the characteristics of the system, pipe system you have, and they will give you the curve in terms of head and discharge. Okay, so you will have a curve in terms of pump head and the Q, but it will give you the idea about the system you have. If you have a system with 5 different types of valve, obviously the minor loss will be very high, right? So this system curve will express that. If you have multiple bends in your system, this system curve will express that. Okay? And the opposite one, which is the pump characteristics curve, that will give you the characteristics of what? The pump itself, right? And usually, I don't know if you have any experience of buying a pump, but if you buy a pump, or just think about any electronics, whenever you buy something, there is a user manual, right? So whenever you buy a pump, there will be a user manual. At the same time, there will be a curve which will give you at which head what discharge you should expect. And that characteristics is the pump characteristics curve. Okay? So the pump characteristics is, I think you already have that, right? In your copy, the definition. Okay, and for pump characteristics curve, we usually have 3 different curves. In total, we have 8 curves, but we will discuss these 3. This is the pump head versus discharge. So this one is H pump versus Q. Sometimes we call the discharge as capacity. Okay. For the second one, brake horse power versus discharge. Do you remember brake horse power? Like we indicate, like it represents what? Yes.
Where should we be writing this down on this?
You can write down on
It's the next page.
here, or I think in next page you have some space. Okay. You can write down anywhere if you have space. Okay. Okay. So, oops. Brake horsepower is actually the indicator for power input versus Q. And the very last one, the efficiency versus Q. There are some other characteristics curve also which we will see, but usually these 3 are the one we will use here. Okay. And you can see here we have one pump head capacity curve. That is the first one here. The next one is power. Next one is efficiency. And you should notice this curve has two vertical axes. The efficiency is on the right side. Okay, so whenever we need to get any value for the efficiency, we will use the right axis. Okay, now I think it's time to differentiate between system curve and pump characteristics curve clearly so that you don't get confused with that one. So let's write down a few characteristics of these two curves. You have some space there. So both of these, they represent the characteristics of their system. So the system curve is, it will represent the behavior of the piping system attached with the pump you have. That means the user have. The pump characteristics curve, it represents the behavior characteristics of the pump you bought from somewhere, or like you have a pump. Curve can be changed based on the piping system rearrangement. Obviously, we saw that we had 5 different systems, like we just discussed, and for each pump, like each system, we will have different system curve, right? But for one single pump, it's fixed for a certain pump. And the system curve is developed by you, engineers or users, like based on your purpose, who is working with the piping system. Pump characteristics curve usually is provided by the manufacturer, and they run thousands of tests with that single pump, and using the data set, they come up with that equation or the curve. Okay, they just plot that and they get the curve and they just give you that. Provides the relation between pump head and discharge. The same thing for pump characteristics curve, provides relationship between pump head and discharge. Plus, it also gives you the relationship between head and efficiency. Head and power. Okay. So we can have this relationship from the pump characteristics curve. Okay. Now, if I ask you some multiple choice questions from here, you should be able to answer that. Let's check that. So the system curve, if all of you have, like if I ask you to do some experiment, okay, what is the effect of friction on flow? And each one has, like I asked you to design your own system, okay? So the system curve for each of you, it will be different or it will be same?
Should be the same since the Z is fixed.
But I asked you to design your own systems and you don't know what others are designing. So it can be
That should change
based on like whatever you have designed, right? But at the end, I told you, okay, I have a pump in the lab and I recommend you use that pump. Like every group should use the same pump and you should coordinate which group will use when. So what do you think? The pump characteristics curve, that will be same, right? Because that is, you are using the same pump, but you have different system for yourself. So that will be different. Okay, great. Next question. Can you be a manufacturer just based on the thing that you need to provide a pump characteristics curve? Can you be a manufacturer? It's the no and yes. No is you can't make a pump here because we don't have the facility, but you can provide a pump characteristics curve if you do 10 tests with the same pump and you come up with the values and plot that. So you can act as a manufacturer also, just based on if you can provide a pump characteristics curve. Okay. Okay. Now few more definition for the pump characteristics curve. So we have this pump characteristics curve here. How many different curves we have here? We have three. One is for head capacity curve, right? One is for power, one is for efficiency, right? Okay, now the shut-off head is the head at which head the discharge is 0. Okay, that is the shut-off head. Yeah, the shut-off head, like at some head, the discharge will be 0, right? If you look at this curve. So at which head the discharge is 0, that is called the shut-off head. Now from this head capacity curve, which point is called the shut-off head? Which one is the shut-off head?
The head capacity curve is 0. Oh, that'll have to be the head.
This is the capacity 0, right? So at this point, what is the head here? 0? Head is 0? See that again. What is the head here? 125. Yes, that means the maximum head, right? Okay, tell me one more thing. Why the curve is going downward, the head capacity curve? What does that mean? With increasing flow, head is what? Decreasing. That's because when the head is very high, the pump has to work against the gravity, right? To get the water. So whenever you have a small head or like shorter head, the pump needs to work less. That's why you will get more flow. Okay. So the free delivery is just the opposite one. It's the one is discharge for 0 head. So that one is actually for head for 0 discharge. And this one is discharge for 0 head. Do we have that point here, the free delivery point here? We don't have that, but we can assume what it would look like. So if I just try to extend this line like this way, and maybe here the flow is 16, 18, 20, maybe 2400. I don't know if that is correct or not. So that point is called what? The free delivery, right? Now, can you tell me what will be the free delivery discharge? What will be the magnitude of that? It will be 2400 GPM, right? Okay. 2 more things we need to know. Oh, we have only 4 minutes. Okay. We can do that. Everyone's done up to this point? Okay. In the back, are you done? Okay. So, few more things. Best efficiency point. So, we call that BEP, best efficiency point. So, from the name, what do you think? What this point should tell you?
At the point where you have the least amount of head.
Least amount of head, or
Yeah, let's go with that.
something like that, like at which point you can get the maximum efficiency, right? Something like that. Okay, yeah, exactly. That is what best efficiency point. So best efficiency point is Q and head corresponding to maximum efficiency. Okay, now from here, what is the maximum efficiency? What is the magnitude of that?
90. The H is 90 and the Q is H is 90.
I think you are. I think you got the next step, I guess. Yeah, I know what you are talking about. Yeah. So the efficiency is 70%, right?
Yes.
Now we need to find What is the Q and H at this 70%? How can we find that? I think you were talking about that one, right? So how can we find the efficiency point, maximum efficiency point, or Q and H at this efficiency? What is the way? Any idea? How can we find the H and Q at this point?
You draw a vertical lines, and where it hits the head capacity.
Great. Yes. So draw a vertical line. Are you seeing that red line here? Okay. So draw a vertical line at maximum efficiency, the red line. That will give you Q and H at maximum efficiency, and those are called BEP. Okay, quickly give me Q and H at maximum efficiency. So this one is the H and this one is the Q, right?
Yeah.
Okay. So this 1300 GPM and 90 feet altogether, they are called best efficiency point. That simply tells you if your system can operate at this point, it will get the maximum efficiency. Okay?
Yes.
Okay. Can I have just 1 minute?
Yes.
Okay, thank you. So the suitability of pump is, it will just give you how close your pump operating point to that best efficiency point or not. Okay, so that is the suitability one. We will start from this point, and yeah, make sure you bring this class lecture on Monday, Friday.
Yes, ma'am.
Thank you, class. I'll see you on Friday, hopefully.